Welcome to the Akbar Academy podcast. Today we're digging into two everyday words, mass and weight, that seem simple but actually shape everything from your morning coffee to missions on Mars.
That's fascinating timing. I just read about how astronauts deal with these forces differently in space. Most people don't realize that their mass stays exactly the same whether they're standing on Earth or floating in the International Space Station.
And here's something mind-blowing. When someone steps on a bathroom scale and says they want to lose weight, they're really talking about mass. That mix-up is everywhere in everyday language.
Totally. The way I like to explain it is this: mass is the amount of stuff you're made of, what physicists call matter. And here's the cool part: your mass stays constant no matter where you are in the universe.
You know what always gets me? The connection between mass and motion, like pushing a loaded shopping cart versus an empty one. That resistance you feel, that's mass in action.
Perfect everyday example. And speaking of real-world situations, let's take this to space.
All right, picture this: an astronaut with a mass of 70 kilograms. On Earth, they weigh about 686 newtons. But on the moon, only about 112 newtons. Same person, same mass, totally different weight.
That's because Earth's gravity is about 9.8 newtons per kilogram, while the Moon's is only 1.6. It's the gravitational field strength that changes the force pulling you down.
And here's where it gets even cooler. On Earth, everything that falls accelerates at 9.8 meters per second squared. Scientists call this the acceleration of free fall.
Classic physics moment: Galileo dropping objects from the Leaning Tower of Pisa to show they fall at the same rate, no matter the mass.
Exactly. And if you drop a bowling ball and a golf ball side by side, assuming no air resistance, they'll hit the ground at the same time. Even though one's heavier, gravity treats them the same.
But throw in air resistance, and everything changes. A feather falls way slower than a bowling ball, not because it's lighter, but because it reaches terminal velocity really fast.
Skydiving is a perfect real-world example. When you first jump, you accelerate at 9.8 meters per second square, but as you fall, air resistance builds up. Once that upward force equals your weight, you stop accelerating. That's terminal velocity.
Then comes the parachute. Huge increase in surface area, tons more air resistance, and boom, you slow way down for a safe landing.
That's such a great example of how these forces play together. And it brings up something most people don't think about. We actually use different tools to measure mass and weight.
Right. For mass, we use something like a mass balance, but for weight, which is a force, we use a spring scale or Newton meter, also known as force meter.
And on Earth, because gravity is basically constant, we get used to thinking mass and weight are the same, but they're really not.
Let's put that into numbers. Say someone has a mass of 85 kilograms. Multiply that by Earth's gravity, 9.8 newtons per kilogram, and you get about 833 newtons of weight.
And that level of precision really matters. It's how engineers calculate force loads, how astronauts train, how we build machines that work safely on Earth and beyond.
It's amazing how these simple ideas affect so much: construction, transportation, even space exploration.
And they scale up perfectly. The same physics that describes a pencil falling to the floor also explains how the moon orbits Earth, or how we land a rover on Mars.
Which creates some wild challenges for space missions. Equipment needs to work under different gravitational conditions, and astronauts need to adjust how they move, train, and even eat.
Looking to the future, I think understanding mass and gravity is going to be huge for space colonization. Whether it's moon bases or Mars cities, everything will need to adapt to those local forces.
It really puts things in perspective. Mass and weight aren't just science class terms. They're the foundation of how we interact with every environment we live in.
And here's the key takeaway: mass is constant, weight depends on gravity. So next time you step on a scale, remember it's not just measuring the stuff you're made of. It measures weight, the force you apply, but shows mass in kilograms because it assumes Earth's gravity. On the moon, you'd weigh less, and that reading would be wrong.
And maybe think about how different that number would be if you were standing on the moon.
Thanks for exploring the forces that shape our universe with us today.
This has been another episode of the Akbar Academy podcast, where science meets the everyday, because at Akbar Academy, we're a class above the rest.